very good morning. So, let's actually conclude on the weighted least squares problem today. Briefly talk about nonlinear least squares, and then I'll do a quick roundup of MLE, and if time permits, we'll just get started on Bayesian. The idea in Bayesian, as far as Bayesian estimation is concerned, just to give you a preview, we may not apply it to estimating time series models. It's going to be a bit tough doing that in this course, but certainly we'll learn in the last week of this course, which is next week, how to now take these estimation methods and apply them to estimating two things: signal properties, mainly ACF and power spectral densities. And in that process, we will also learn what are whiteness tests, and then we will learn how to apply these estimation methods to estimating time series models. Once that is done, then we will close the course with a brief discussion on forecasting, on prediction. After all, we have come all along only to forecast, and it will be a pity if you do not know how to predict once I have estimated a model. We have visited those concepts in bits and pieces all along. It is just a matter of putting them together and formalizing certain concepts, but otherwise the basic result on prediction has already been given, which is a conditional expectation is the best prediction, but then some more discussion on that is required. So, let us get going on weighted least squares. I have already introduced to you the concept of weighted least squares and given you a few compelling reasons as to why one would be interested in formulating and solving a weighted least squares problem. Mainly for whatever reason you would like to attach different importance to different observations. It could be motivated by heteroskedasticity, or maybe correlation in the errors, or many a times there is this need for updating the model. So, when you are updating your model online, then the brute force thing is to take the entire data from the time you started modeling to the present and rebuild your model. That means re-estimate your theta. Obviously, common sense tells us that we may have to give more importance to the most recent data and downplay the data that is in the past. And for this reason, there is a concept called forgetting factor. We all have our forgetting factors inbuilt into us when it comes to learning, remembering concepts. But when it comes to modeling, unless you include that forgetting factor, it will not forget the past. So, this forgetting factor can be thought of again as a weighting. So, there are several scenarios in which we may want to formulate and solve a weighted least squares problem. And yesterday I said that the weighted least squares problem can be solved very easily by recasting it as an ordinary least squares problem, and that is exactly what you see on the slide. Because W is positive definite, and I have already told you why the weighting matrix should be positive definite, that is to preserve the convexity of the objective function. We can perform a Cholesky factorization and scale both the observations and the regressors accordingly, right. So, the weighting factor determines the scaling, and the nice thing is now in terms of the scaled data, we have an OLS. So, the WLS is nothing but an OLS on scaled data, but the scaling factor being governed by W. Since we already know the solution to the OLS, we can straight away write the solution to the weighted least squares. All one has to do is, instead of phi, use phi subscript s, and instead of y, use y subscript s, and then plug them back in. So, if you see this expression here, instead of phi s, we would substitute here c times phi, so as to be able to write the solution in terms of the original data, not the scale data. So, that is it. So, you have here phi transpose w phi inverse times phi transpose w y, which is not a difficult solution to remember, and straight away you should verify that when W is identity, you recover the OLS solution. Okay. And what we will do is we will try to now ask what governs the choice of W, right. And before we do that, let me also tell you that as we have arrived the solution by scaling the data, we have also implicitly scaled the errors. Okay. So, what we are saying is, here is the original model, linear regression model. So, let us assume I have gotten everything right. What we are doing by scaling y and psi, we are also actually scaling the errors. And that is the trick, and this is a standard trick that you will see prevailing in parameter estimation. Whenever the errors do not meet the criterion of ordinary least squares, then one way out is to scale the errors. But of course, the big issue is knowing the weights a priori. Okay. So, here we are saying that these errors do not satisfy the conditions that are ripe for ordinary least squares. What are the conditions that are ripe for ordinary least squares? They should be white. Whatever you have left out in your regression model should be white, right. That is when only your prediction, we have been all along using the predictor as this. So, this makes sense only from this perspective as well. Using this predictor makes sense only when what you have left out is white. If what you have left out is not white, obviously you should factor that into your prediction. Remember, although I am writing here y hat of k, implicitly you should understand that this y hat of k is given psi k and theta. Normally we do not write this, but it is to be understood that I am given the regressors, I am given the theta, and hence the prediction. In time series models, your regressors are past data, and therefore your y hat becomes typically one step ahead prediction. All right. Now, if this was not white, then the one step ahead prediction is not going to be 0. And again, from that perspective, you want to make sure that what you have left out is white. So, coming back to the point, if you know for some reason that what you have left out is white, and you do not want to really model this part, and you are only bent on estimating this theta. So, as an example, suppose these are white, these are colored, but they are not necessarily white in the definition sense. Remember, white noise process is a stationary uncorrelated process. The moment Z has heteroskedasticity, the stationarity property is gone. It is still uncorrelated, that is temporally, but it does not have the stationarity property. In such cases, what you are saying is, I know that the Zk can be written. So, when I have heteroskedasticity, maybe we could write this as alpha k Ek, where Ek is now a stationary, your classical white noise process, and alpha k is a scaling factor that keeps changing with the observation or with the index. And what we are doing by scaling is essentially, remember, as you will see shortly, for the heteroskedastic case, the weighting matrix turns out to be the inverse of this noise covariance matrix. Okay? And you will see essentially that your W's would be inverses of alpha. That means your W would be a diagonal matrix of 1 over alpha. If you did not know the weighted least squares problem, let us say you did not know the formulation, all you knew that OLS works best for the pure white noise case, then if you are given that Z has this kind of a structure, then what you would do is, if you are given alpha, you would rewrite this in this way, 1 over alpha k yk times 1 over alpha k theta plus Ek. So, you would rewrite the same equation given alpha k in this fashion. Now, you define a new y and a new regressor. That new phi and a new y and new regressor is nothing but your scale data. But what this point also says is that in that process you have rescaled your errors, such that now in the scaled domain the errors meet the requirements for the OLS to work for you. OLS will work, but it works best, that means it will give you the most efficient estimates when the residuals are white or your noise is white. So, that is the basic idea you should keep in mind. As we are scaling the data, we are also scaling the errors in a particular fashion. So, the question is now how to choose the weighting matrix W. Who gives me this? Do I know alpha case? For example, this is in the heteroskedastic case. There are, as I have already said, many other situations in which we run into a WS formulation. In all such formulations, how do I choose W? Now, there are many considerations that can go into it, but primarily there are two. One is model updation, okay, where W is a diagonal matrix of forgetting factors. What we mean by forgetting factors is you would have your objective function as follows. Instead of simple y k minus psi transpose k theta square, you would have a lambda power n minus k. Let us say k runs from 1 to n or 0, you can also modify this accordingly. So, the idea is here lambda is a forgetting factor, it is a positive value between 0 and 1. So, that the most recent data, that is when k equals n, lambda is lambda power n minus k is 1. So, the most recent data is given the maximum importance, and the last one, that is the first observation k equals 1. If you are standing at n, then the past one, which is really remotely in the past, is k equals 1, that is given the least importance because lambda is a factor between 0 and 1. So, this is the concept of forgetting factor. You can straight away now recognize what is W. What would be W here? It would be a diagonal matrix, and what would be the entries here? Lambda. The first one would have n minus 1 up to lambda power 0, right. All right. So, that is the case when, so when you are looking at model updation using the concept of forgetting factors, W becomes a diagonal matrix of forgetting factors and lambda is a user's choice. There is nothing much there, you decide how much importance has to be given. But a far more important and prominent consideration is to obtain efficient estimates, because that is how we started off. Remember, we said that ordinary least squares does not work when z is not white, when the equation error is not white, and then we set on to the weighted least squares formulation. So, obviously, that consideration has to be now taken into account, and the question to be asked is what is the W, what is the weighting matrix now that will guarantee efficient estimates. When you are looking at a heteroskedastic case, it is very obvious what is W. If I knew the variances of z, if I knew the variances or if I knew alpha k, all I have to do is what would be W? Diagonal matrix of 1 by alphas, very good, right. Stating that if alpha is high, then that observation should be given lower importance. Obviously, if one observation, if alpha is high for a particular k, then that observation has a larger error. Suppose alpha k is the highest for that particular observation, then that observation has the largest error among all the observations, and obviously you want to downplay that observation, right. So, W will be inversely proportional to alpha. So, you get some idea now that for obtaining efficient estimates, we need to have W as the inverse of the noise covariance matrix. That is, if I were to look at the noise covariance matrix of Z in this case, it would be simply a diagonal matrix, but let us assume sigma square E is 1, then I would have alpha 1 square up to alpha n square, right, and W is going to be simply the inverse of this. Remember, I am scaling the data by with 1 over alpha. And when I move on to the objective function, when I rewrite the objective function now in terms of this scaled observations and regressors, it amounts to writing an objective function for the original data using a weighting of 1 over alpha square, because there is a square there. So, this leads us actually to the answer, but theoretically the way you would arrive at this solution, that is to the question what should be the weighting matrix W if I want the most efficient estimate, and efficiency has got to do with the variance. So, you can show that in a similar way that we have shown earlier for the OLS, the sigma theta hat is nothing but that is for the weighted least squares is this simple looking expression here. Okay. So, as you can see here, it is a very simple expression. I do not expect you to remember this at all, even I have tried remembering it many times, but failed, too many W's and phi's and so on. But what you should quickly check is if W is identity and Z is white, it simplifies to the OLS expression that we had seen, sigma square E times phi transpose phi inverse. Now, what people have done is taken this simple expression in days where there was a lot of time and asked what gets me the minimum value of this. This is a matrix, so it does not make sense to talk of minimum of sigma theta hat. People have looked at minimizing the trace. What is trace? Sum of diagonal elements. So, they have looked at that and essentially come up with this answer that the optimal W is nothing but sigma Z inverse, which is what intuitively we expected. Our arguments were based on the heteroskedastic example, but this is there is a formal proof available, just look up the literature. It is not of interest to us at this moment. We argue without any debate that this is a correct solution, we agree. So, intuitively we know that the solution makes sense. Of course, the big question is who gives me sigma Z? It is a very rare commodity, you can't find it online, nowhere you have to get it from data. And that is the typical approach that is used in all weighted least squares or any weighted approach where your weighting matrix depends on the noise covariance matrix. But look at how important understanding this entire theory is. This one equation should help you appreciate the need for a formal study of the subject. If you did not know any of this, you would be performing ordinary linear regression on data which has probably heteroskedasticity or errors are not white and so on, and assume that your fit is best, that the model is good. But the fact is you should have worked with scale data. In fact, there is a whole lot of literature and we are continuing to work on it in a slightly different framework. We have using these ideas, we have some really breakthrough solutions very recently in our group, and now we are trying to communicate that to the world. So, this simple idea of weighting and incorporating that in the regression, and that the fact that this weighting depends on the noise covariance matrix of the errors should really help us appreciate the beauty of this formalization. In fact, I told you the noise covariance matrix is perhaps, or just the covariance matrix, you have been seeing it coming time and again in the course, is perhaps the most ubiquitous quantity that you will keep encountering all through your life in data analysis. There is no escape to it. Even when you are in the nonlinear world, the covariance matrix will come and haunt you, or to help you with your data analysis in fact. So, let us look at an example to understand the beauty of this result. By the way, so when you choose this weighting matrix, it turns out that the sigma theta hat in the weighted least squares case turns out to be this expression here, phi transpose sigma E, phi transpose sigma Z, phi inverse. Okay. So, that is what is the answer, and once again you should check when Z is white, what happens? Sigma Z will be a diagonal matrix of sigma square E's on the diagonal, and you recover the OLS solution, and that anyway we know is the most efficient, right. So, it is just a corroboration of what we already know, but it is a good practice to keep checking so that you know the expressions that you are working with are correct. Let us look at an example. We have already talked about this. So, this is an example as pertaining to what I discussed earlier. There is a reactor and temperature measurements are being made by 10 sensors. Let me tell you also, this is a synthetic data, but representative of a realistic scenario. So, definitely I have cooked up the data, but this is not something very rare. You will see this kind of situations quite often. And what I have given you in this case is the sensor variances. So, here the K for us is not time, the K for us is sensor. So, I have 10 sensors and I am supposed to estimate the average. If I did not know anything, as a layman I would take simple mean or sample mean of this 10 sensor readings and get the reactor temperature. The assumption is that the reaction temperature is constant during these experiments. But suppose I were to give you the variances of each of these sensors, it is possible to obtain those in this kind of experiments. For example, say if I know the process is at steady state, then I can observe the sensor noise in each sensor and estimate the variance and report them. So, imagine that that is how I have done it and the variances have been given. So, now the goal is to estimate the steady state temperature. As I said, the simple solution is the least square solution, which is sample mean. But now that I am familiar with the weighted least squares concepts, I would rather construct a weighted average. That is something that you should remember, that when you are going to when you are having heteroskedastic errors and you are estimating mean, what you would be working with for an estimate of mean is a weighted average. And how does that come out to be? Because W, we know optimal W is 1 over sigma square along the diagonals, and all you have to do is plug in to this solution here, phi transpose W, phi inverse, phi transpose Wy. In every problem, until you get used to it, you should make it a habit to recognize what is a regressor, what is the data. The data Y is the data given to us. The regressor in this case, because I am estimating an average, remember the problem of interest to me is that Y, our familiar problem, C plus Zk. Instead of Ek, I have Zk. So, this C is the unknown that I am estimating, that is our theta, but there is no regressor. However, always there are these two numbers in math, 1 and 0, which are invisibly present in some form or the other in every number, right. So, 1 is the invisible regressor there, and that is what makes up my phi. There is only one regressor. So, what would be phi transpose, or let us say phi itself? It will be a column matrix of ones, correct. As a result, phi trans and W we anyway know is a diagonal matrix. So, essentially it amounts to this expression here. So, phi transpose W phi inverse would be your denominator, because W is a diagonal matrix, and phi transpose Wy would be the numerator, again because W is a diagonal matrix. Phi transpose would be a row vector of ones, got it, and that is all. So, the phi transpose here is the one that is responsible for the summation that you see, right, and this Yk by sigma square sigma square k comes about by this multiplication W times Y. All I straight away recognize is I am constructing a weighted average. Now, the value turns out to be 62 point something, and the variance can also be computed. Remember, we said when we choose W to be the inverse of noise covariance matrix, then the variance is simply phi transpose W phi inverse, and once again I compute that to be 0.0805. Now, why did we go through this weighted least squares approach? Because we thought this gives me better results than the least squares approach. Better in what sense? Efficiency. What does efficiency mean? Variance should be lower than another one. So, we should expect WLS to be more efficient. then the least squares. The question is if it is. So, let us look at this here. First of all, look at the point estimate. Now, this is where the need for computing the variance also is highlighted. So, you look at the point estimate, is it significantly different from the point estimate that we computed with the weighted least squares? Not much. This gives me 61.95 something, that gave me 62 point something, right. So, if you look at the difference in point estimates, it is not much, but if you look at the variability in the estimate, what do you notice? Here you have 0.16, right, and whereas here you have 0.08. So, the variance of the weighted of the ordinary least squares is twice the variability that you see in weighted least squares. If you translate that in terms of standard errors, it is 1.41 roughly, right. That can be quite a lot in many applications, but also let me tell you that in this example the factor turns out to be 1.41, that is in terms of errors. In some examples it may be much higher than this, in some other examples it may be lower than this, but you are always guaranteed that weighted least squares will not perform worse than OLS. At best it will be OLS. So, you do not lose much by working with WLS, but what you can lose out on is the computational time, because it is an iterative, typically W is not known, you have to iterate and therefore, you have to put in some effort. The question is whether that effort is worth it, right. You may not know that a priori, sometimes you may know, sometimes you know clearly there is a need for weighted least squares. So, you say yeah, it is worth the iteration. Sometimes you say it is okay, there is heteroskedasticity, but the fluctuation is very, very low, more or less I will treat it as a homoskedastic case. I will sacrifice a bit of efficiency in the estimate for computational efficiency. So, there is this conflict between computational efficiency and estimate efficiency. So, those are the standard things that you will come across in estimation. So, hopefully this example gives you a better picture of how weighted least squares works and the inner workings of it.